Hello everyone, let us see the basics behind electric field intensity. For understanding this, we have to take a constellation where a point charge Q or Q1 at the center of a sphere. If any other similar charge or opposite polarity, whatever it may be, similar charge Q2 is brought near the particular Q1, surely Q2 will experience a force. Okay? Even if Q2 is moved around at the same distance at all other points around this Q1, a similar force is experienced by Q2. So, we come to a conclusion that there exists a region around a charge around Q1 in which Q1 exerts a force on any other charge brought nearer to it. This region where the particular charge exerts a force on any other charge located or brought into the region is called as E field, electric field of that particular charge. Which charge? In this case it is Q1. How to estimate it? We have to look at the force experienced by Q2 due to the force generated by Q1. It's computed using Coulomb's law, which is given by Q1 by Q2, or Q1 Q2 by 4 pi epsilon naught into magnitude square of the distance between the charges Q1 and Q2. And of course, it is a vector quantity, so it indicates the direction, unit vector indicates the direction in which the force is acting along. It's a very simple calculation because in the total estimation you have to find out only AR12. Once you determine AR12, automatically, because AR12 is a unit vector which is computed based on the ratio of vector by the magnitude of the vector, so you can easily calculate the force acting on Q2 due to Q1. This is how represented by me in the class Q2, Q1. Q1 exerts a force on Q2. Okay? Who is responsible? Q1 is responsible. Who exerts a force on Q2? Q1 exerts a force. So, force per unit charge. What is it? So, ratio of F2 by Q2 is equal to, Q1 divided by 4 pi epsilon naught into the magnitude square, the distance, the square of the distance, and of course, it is a vector quantity, it is acting along the line joining, so the direction is indicated by the unit vector. So, the force exerted by the unit charge is called electric field intensity or electric field strength. I'll explain it again. Force exerted by Q1 per unit charge is called electric field intensity, or I can mention this as electric field strength. Okay, it's a vector quantity, I just told you. So E, mathematically it is expressed as electric field strength is the strength of Q1 because it exerts a force on Q2. Electric field intensity of Q1 is equal to, it's the ratio of Q1 divided by 4 pi epsilon naught R1P if it acts on any other charge which is brought nearer to it. So I should take the magnitude, square of the magnitude of the distance, A1P, because P indicates position of any other charge placed around Q1. I have already told you there are two charges. One is Q1, the other one is Q2. the line joining the distance between these two charges is indicated by R12. Okay, where AR is the unit vector. Okay, AR is the unit vector, AR or AR12. And what is the amount of force exerted on Q2? F2. If Q2 is 1 coulomb, then it is indicated as E, electric field intensity. So due to a single point charge Q1 in free space or a vacuum is given by E exerts a force on Q2. If Q2 is 1 coulomb, then I say it is the electric field strength of Q1 which exerts a force on Q2 is equal to 4 pi epsilon naught R squared or R12 squared A12 unit vector. Any other definition of electric field intensity is also considered in our subject because it is the force experienced by the unit positive charge. You can also mention it this way. Okay, so if Q1 is located at the center of a spherical coordinate system and AR is the radial vector in the spherical coordinate system, if I keep Q1 at the center of a sphere and around the sphere, what is the sphere having radius R, AR squared will be along the radial direction. Spherical coordinate system where Q1 is located at the center of a sphere having R as the radius. Good. Now the unit of electric field intensity of Q1 will be represented as Newton per coulomb, but is also measured in terms of volt per meter. Practically this is what we use. I just move further. Consider a point charge which is located in a Cartesian coordinate system like this, x, y and z. I just take a point charge Q like this, which is located at a coordinate x1, y1, z1, and other point charge which is located at Q2. Let me say this is Q1 and the other one is Q2. The coordinates at which it is located is x, y, z. So I just take this, okay, straight line. Sorry if it is not properly drawn. R is the distance vector. The unit vector is indicated by AR, right? And as you all know that this force will be acting along this line joining electric field intensity. But I just want to tell you one more important information. Whenever you just take the coordinate system and 2 points, obviously you should know the position vector of those 2 points. So position vector of A and position vector of B. Okay, this is indicated by here. What is this? Let me call this as A vector. This is indicated by B vector. Other, I can say for example, RA is represented as position vector. RA, point RA is located from origin. So RA is A vector and RB is B vector. Okay. So A vector is given by x1 AX plus y1 AY plus B Z1 AZ. Whereas another vector B is indicated by simply x AX, because look at the coordinates, y into AY plus Z into AZ. Okay. So when you want me to calculate the distance difference or the distance between the point B and A, I can just calculate it as distance vector B minus A. When you take B minus A, how will you express it? It is expressed as x minus x1 AX plus y, because B minus A, y minus y1 AY. Yes, last component will be Z minus Z1 AZ. Okay. Yes. Once you know R vector, I just want you to go to the computation of AR vector. It is the unit vector based on which the direction is estimated. So B minus A by modulus of B minus A. Okay. So E at any point where any other charge is located can be estimated, because Q1 is the charge located at point A, and because did you know this is Q1 is the point charge located at A, point A, and Q2 is the charge located at position B. Q1 divided by 4 pi epsilon naught R1 squared or R squared I just take the magnitude square and AR vector. So Q1 by 4 pi epsilon naught R squared simply, and this is actually represented by vector R by modulus of vector R. This AR is represented as the vector, corresponding vector divided by magnitude of the vector. The unit is already specified as volt per meter. Okay. In some cases, you may have to simply estimate only the magnitude which is acting along, or which is exerted by Q1 on Q2 at a point B, which will be simply taken as Q1 divided by 4 pi epsilon naught R squared. Okay, R squared volt per meter. Right. Electric field intensity. So due to discrete charges, for example, we have charge 1 Q1, another charge Q2 is located. There is a third charge located along this line Q3. As we have discussed in the class, there is another charge Q4. There is what like this n number of charges Qn, Q1, Q2, Q3, and Q4. There are 4 charges. Each is at a distance of, say, for example, R1 vector. The second distance vector is R2. The third distance vector is R3. The fourth distance vector is mentioned as R4. The nth distance vector is mentioned as Rn. And if you want me to indicate the direction, I just mention it with the help of AR1. Whereas the direction is AR2, unit vector along second vector. And this is the unit vector along vector 3. This is the unit vector along fourth vector. And this is the unit vector along ARN, because it indicates only the direction. So at point P, the total force, point P, the force exerted on a charge due to n number of charges present around it, because it is a vector sum of individual forces exerted by individual charges. So the electric field at a point due to n number of charges surrounding it will be applied or obtained with the help of superposition theorem or superposition law. Consider n number of charges Q1, Q2, Q3, Q4, Qn. The combined electric field intensity at point P, having known the distances from each charge Q1, Q2, Q3, Qn is given as R1, R2, R3, R4, Rn, and the unit vectors. So the total electric field intensity at a point P, from the receiver point of view, at point P is the vector sum of individual electric field intensity. So E1, E2 and E3, etc. The last one is nth component. So which is given as Q1 divided by 4 pi epsilon naught R1 square AR1. Second one is Q1 is the source, right? Q2 is the source. So 4 pi epsilon naught R2 squared and AR2. Like this, the last component will become Qn divided by 4 pi epsilon naught Rn ARN. Okay? So if you take the total electric field intensity E is given by 1 by 4 pi epsilon naught multiplied by the summation. So I varies from 1 to n. Qi divided by Ri squared ARN. So where Ari is actually the unit vector indicating the direction vector of Ri vector. That is from any other point P, position vector point P to Ri. You have to find out. And to that of the magnitude of this Rp bar minus Ri bar. Okay. These are all the general concepts regarding point charges. But forces and electric fields due to only point charges are discussed so far. In addition to point charges, there is a possibility of continuous charge distributions like line charge, surface charge and volume charge. Point charge, line charge, surface charge, the last one is volume charge. Surface, dimensions of the surface carrying a charge are very, very small. Then we will call it as, obviously, region surrounding it, then the surface can be treated to be a point charge in fact. The corresponding charge is called as point charge. It has a position, but the surface surrounding it is very, very, very small, so we call it as point charge. Say for example, we used to mention Q1 or something like Q minus Q2 or something like this, Q3. So dot, even the dot should not be of larger dimension in fact. It must be a point charge, only 1 point, see, 1 point, that's it. So I just now move on to line charge. It is possible to view charges as distribution of charges along a straight line or any other piece of wire or an antenna. Just view this as line segment over which the charges are said to be distributed with rho L line charge density. So if this is a straight line or an arbitrary line. Charge density in the line charge is denoted as rho L. Charge density of the line charge. Charges per unit length. This is indicated as charges per unit length. Understood? Okay. What is it? It is estimated as total charges in terms of coulomb to the of total length. Okay. Rho L, charge density, line charge density, whose units are coulomb per meter. Similarly, if you ask me to find out the charges present, total amount of charges present, because I can say, having considered dl as a segment length, having rho L as a charge density, so rho L dl is equal to the total charge present in it, dq. Charge on a differential length is given by dq is equal to rho L dl. That's what I told you. Rho L is the ratio of dq by dl. Charge in coulombs to that of total length. Considering an elementary portion or differential line segment, it is actually rho L is equal to dq by dl. Charge on differential length. So, if from this, if you ask me to find out what is q, I should always go for integration of dq over L, and this is represented as dq rho L dl. Okay, dl. The line length is closed line in or closed path. Obviously, we used to say q is equal to integral becomes a closed contour integral, so it is represented as closed contour integral of rho L dl. So rho L dl within integration will provide me the total charge. Okay. Similar to this one, surface charge, sheet of charges. For example, I have a random sheet surface over which the charges are said to be present. Charges are present on it. Distributed. Charge is said to be distributed uniformly over a two-dimensional surface, arbitrary surface. Then it is mentioned as sheet of charges, surface charge, sheet of charges. So two-dimensional area in terms of square meters. So rho S, what is rho S? Rho S is equal to total charge in coulomb to the total area, right? Q by total area. In the previous case it was total length. Here this is total area in terms of meter square. So we used to indicate this as coulomb per meter square. Q by area. So in case of surface charge distribution, it is necessary to find the total charge, usually. Total charge by considering the elementary surface first and then expanding this dq concept, because dq is determined by dq present over ds. The ratio of dq by ds will provide me rho s. So dq is considered as rho s ds. Okay. So integrating this dq over the given surface, open surface, q is equal to surface integral of rho s ds. Surface integral is mathematically expressed like this. The plate of charged plate, in the sense charges. Parallel plate capacitor, a plate full of charges, is an example of surface charge distribution. So the best example is parallel plate capacitor. Parallel plate capacitor. So when you consider charge distribution, for example in a volume, uniformly charges are said to be distributed. I just think of taking a cylinder for this matter. I take a cylinder, freehand diagram. So just assume that this is a cylinder, random cylinder, and you can see that the charges are said to be fully distributed and uniformly distributed throughout the cylinder. The volume full of charges. Charge distributed uniformly in a volume. Then it is called as volume charge density. Volume charge. So volume charge density is denoted as rho V. Okay? Rho V. Defined as, because rho V is mentioned as, in the previous case it was mentioned as rho S. In the previous case it was mentioned as rho L, rho S, line charge, surface charge and volume charge. So you can take it as total charge present in a volume in terms of coulomb divided by total volume. By considering the charge present in a volume dq in a small volume dv, surface charge density can be identified as rho V, whose units are coulomb per meter cube. So total charge within a finite given volume, if you want me to obtain, so by integrating dq I can obtain. What is this dq? When you integrate it is equivalent to say integral rho V dv, but this is obtained or this is performed over a volume. Charged cloud is an example for this. So occasionally point charges are considered for analysis, whereas in many cases electric field intensity, we'll come back to this title, electric field intensity due to a point charge, which is mentioned as Q divided by 4 pi epsilon naught, which is actually considered to be the force acting exerted on any other charge. So the distance between those 2 point charges will be treated as R vector. The magnitude of the R vector is R square. So AR is the unit vector, right? AR is the unit vector. So if you imagine or consider a line charge distribution having surface charge density or line charge density as rho L, as we have told you already, dq is equal to rho L, dl is the simple expression. So differential electric field at any point P due to dq, if you ask me to calculate, I would say it is obtained from the integration of rho L dl with respect to 4 pi epsilon naught into R squared multiplied by AR vector. This is the electric field intensity. Or I will even say, because this is only dE, right? dE. So I don't take integration here. If you ask me to find out what is the electric field intensity at a point P due to line charge, okay, total electric field intensity at a point P due to line charge can be obtained by taking the integration rho L dl divided by 4 pi epsilon naught R square. Right. Because the unit vector you see AR and the differential length line segment is dl, these two will be different for different coordinate systems. These two will definitely depend on coordinate system. Okay. E due to surface charge, for example. Or in the previous case, if you want me to explain with the help of a diagram, I am ready to say, see, I have a straight line or any other conductor over which charges are said to be present, distributed uniformly with the charge density rho L. I take only a small portion which is called as dl. I just assume that the dl is available. Okay, this is the small portion dl which we consider over the line, and now I just take a point P. The point P is the point at which 1 coulomb charge is present or the electric field intensity is going to be observed. Obviously, I just indicate the distance vector as R vector, and you know very clearly that the unit vector is indicated as AR unit vector, which indicates the direction. So electric field intensity will be acting along this line, which is defined as E. You can find out. This E is computed as total electric field intensity at a point P due to differential line segment is dl or dE. Now if you calculate the total electric field intensity because of the total straight line conductor, obviously it is computed as rho L dl divided by 4 pi epsilon naught into R square AR unit vector. This law is applicable for any other charges. In fact, surface charge density, I have a sheet of charges, sheet full of charges are said to be uniformly present in it with rho S as surface charge density. I just imagine a small area which is called as ds. I just assume a point P at a distance R vector whose unit vector is indicated as AR unit vector, and if you calculate the total electric field intensity at a point P is estimated as E is equal to, yes, total electric field intensity will become, instead of Q will be replaced by rho S ds. So when you integrate rho S ds in case of a sheet of charges, it is rho S ds divided by 4 pi epsilon naught R squared into the vector AR unit vector. Similarly, I can go for a volume where the charges are said to be present, uniformly distributed. I just take a small box or any other shape, yes, in which the charges are said to be present, and its volume is dV with volume charge density rho V coulomb per meter cube, because you know dq is equal to rho V dV, right? So different at a point, for example, P at a distance of R vector, if you ask me to calculate what is the electric field intensity, is given by dq divided by 4 pi epsilon naught R squared and the AR, and the dq can be replaced in the case of volume charge density rho V dV divided by 4 pi epsilon naught into R squared AR vector dE. So if you calculate what is E at a point P, it is given by volume integral of rho V dV divided by 4 pi epsilon naught r squared into AR vector. Did you notice in all these cases, due to point charge, due to line charge, due to surface charge, or it may be due to volume charge distribution, electric field strength of a particular charge distribution at a point P is purely determined based on the charge to the of 4 pi epsilon naught into r squared. Right? Thank you.